Hello everyone. In this session, let me continue the theorems on measurable function. Here is a statement. If f is a function defined from E1 union E2 to the set of real number R, where E1 and E2 are two measurable sets. So given that a function f is defined an union of two measurable function E1 and E2. Clearly it was clearly mentioned E1 and E2 are measurable sets in a real number. Then the function f is measurable if and only if f restriction on E1, or we can pronounce this as f restricted to E1 and f restricted to E2 are measurable, or we can say f with respect to E1 and f with respect to E2 are measurable. Fine. Now what is the given theorem is, suppose if this is a function which is measurable, where E1 and E2 are again measurable sets in R, then we have to prove this condition satisfies, and at the same time converse also we have to prove. If this condition satisfies, again we have to prove f is measurable. Now let me prove the theorem. Let us suppose that f from E1 union E2 to R is measurable. So I have taken the first part of a theorem as true. So I have taken f is measurable. Now I have to prove f with respect to E1 or f restricted to E1 and f restricted to E2 are measurable. Fine. So this is what we have to prove. We have assumed f is measurable. We have to prove f with respect to E1 and f with respect to E2 are measurable. So before getting to the theorem, I'll just revise the concept of measurability of a function. So as per the definition of measurability of a function, any function f is measurable on E, then we can write for any real number alpha, I can write an element x belongs to E such that f of x is greater than alpha is also measurable. I have already defined the definition of what we say measurable function. So four conditions, we can also say that as characterization of measurable functions. I have proved the four equivalent statements. So from the statement I can define a measurable function f as f is measurable on E, then for any real number alpha we can write like this. Fine. So now I am trying to apply this definition for a given statement. Clear? What is the given statement? We have assumed that f from E1 union, in this case f is defined from E to R, where E is open in a real number. So in this case we have, in place of E we have E1 union E2 in R is measurable. So since it is given f from E1 union E2 to R is measurable, therefore I can write for any real number alpha or for any alpha belongs to R, I can write a set as x belongs to, in place of E what we have to write, when f is measurable on E I am going to write like this. Since f is measurable on E1 union E2, so I have to write this as x belongs to E1 union E2 such that f of x is greater than alpha is also measurable. This is as per the definition of measurability of a function. Why? Because we have assumed f is measurable. Now I have to prove that f with respect to E1 and f with respect to E2, or f restricted to E1 and f restricted to E2 is also measurable. Right? Now suppose this is the given statement. As for the given statement, it is measurable. It is already given. Now I have to prove x belongs to E1 with respect to E1, meaning is f with restricted to E1 meaning is x belongs to E1 such that f of x greater than alpha is also measurable. We have to prove. It is just a logic. It is easy to remember. I am telling you hint here. So if f is measurable, f is restricted to E1 measurable is same. So f is restricted to E1 measurable, we have to prove. In the sense, I have to prove that for any element x belongs to E1, f of x greater than alpha is measurable. It is sufficient to prove this set is measurable. It is equivalent to f with respect to E1. Now I can write this as x belongs to E1 union E2 such that f of x greater than alpha intersection with E1, I can say. Why? Because you can look here as x belongs to E1 union E2. X belongs to E1 union E2. I have taken intersection with E1. Fine. So this is what I have. It is just for your reference. When I am going to take as per the properties of set, when I am going to take union of two sets, I have to write the first set here. So I'll get E1 here. E1 intersection E1. Again, when I'm going to take intersection, when you're going to take union, you have to take first element as per that I have written. So when I'm going to take intersection, you have to write the second element, so you will get E1 only. So I have rewritten the statement x belongs to E1 as E1 union E2 intersection with E1. Now you can clearly note that as per our assumption, first set, that is x belongs to E1 union E2, here you have. So it is measurable, and moreover we have intersection with E1. E1 is always measurable, it is also already given in the statement. So E1 and E2 are measurable, it is given. So E1 is also measurable, the set is also measurable. So intersection of two measurable set is measurable. We have already proved the theorem. Intersection of two measurable sets is measurable. So as per that I can say the terms in right hand side RHS is measurable. So if RHS is measurable, I can say the term which is in LHS is also measurable. Thereby I can say that therefore x belongs to E1 such that f of x greater than alpha is measurable. Or else in other statement, in another form I can write f restricted to E1 is measurable. Clear? Similarly, since I have proved it for E1, the set E1, I can also say similarly I can prove for f restricted to E2 is also measurable. I am just repeating once again. So first I have assumed is I have taken a statement, given statement, that is f is measurable. So f from E1 union E2 to R is measurable. Now I am going to prove f restricted to E1 and f restricted to E2 are measurable. Fine. So as per the definition of measurability of a function, if any function f defined from E to real number is measurable, then we can say for any real number alpha, this set is measurable. As per the characterization of measurable function, I have proved this theorem also. Fine. So as from that definition, I have chosen that f is E1 union E2 to R. So I have replaced E with E1 union E2. So this is measurable as per the definition of measurability of a function. Now I have to prove that f restricted to E1 is measurable. F restricted to E1 can be written as x belongs to E1 such that f of x greater than alpha. Now x belongs to E1 can be written as E1 union E2 intersection E1, right? So here I have simplified. So when you're going to combine all this, you will get E1 only. So I have rewritten this in this form. So intersection, this is measurable as per the assumed data. Moreover, E1 is measurable, it is given in the theorem itself. So it is intersection of two measurable sets. Intersection of two measurable sets is also measurable. So what I have obtained is the terms here, that is RHS side is measurable. If the terms in RHS side is measurable, I can say the term in LHS is also measurable, that is this set is measurable. Simply I can represent this as f with respect to or restricted to E1 is measurable. Similarly I can prove f restricted to E2 is also measurable. Fine. So direct proof is completed. Now let me prove converse part. So how can I prove converse? Let me write here conversely. So when I'm going to assume converse, let me assume this is true. Second statement is true. Let f restricted to E1 and f restricted to E2 is measurable. So I have to prove that f defined from E1 union E2 to R is also measurable. This is what the converse part is, right? So I have assumed this. So what I have assumed is f with respect to E1 or f with restricted to E2 is measurable. So let me denote G1 as f restricted to E1 and G2 as f restricted to E2. Fine. Now you can clearly note that I have to prove this is also measurable. Now I have to prove, meaning is that, let me write here E1 union E2 as per the definition of a measurable function. What I can write, x belongs to, in order to prove this E1 union E2, it is just for your reference what we have to prove. Idea should be there. So that is why I am telling you f of x greater than alpha is measurable. If you prove this statement, it is true that f is measurable, right? So I have to prove this. Now let me rewrite this as, consider this x belongs to E1 union E2 such that f of x greater than alpha. Now I can write this as, see here I am going to rewrite this as, I am going to just rewrite this as like x belongs to, since x belongs to union of both E1 and E2, so I can split this as x belongs to E1 such that like g1 of x, I am going to take g1. Why? Because I am talking only with reference to E1. So let me take a function with respect to E1 is g1. So g1 of x is greater than alpha union x belongs to E2 such that g2 of x is greater than alpha. Fine, I can rewrite like this, right? Since I have to prove this is measurable, so I am going to express this as, I have splitted this. Why? Because as x belongs to E1 union E2, I can write x belongs to E1 and x belongs to E2. I have splitted this. Now you can note that the terms in RHS, so I have expressed this as union of these two. So in the terms in RHS is measurable, right? Why? Because this is a function with respect to E1 and the function with respect to E2. Both are measurable. Why? Because it is from the assumed statement. So if both are measurable, I can say their union is also measurable. I can say union of measurable functions. So union of measurable function is again measurable. So if RHS is measurable, I can say LHS is also measurable. Therefore, I can clearly say x belongs to E1 union E2 such that f of x greater than alpha is also measurable. Meaning is f defined from E1 union E2 to R is measurable. So this is what we have to prove. Converse part is clear, right? So only thing is you have to remember the definition of measurability of a function. Hope so it is clear. Here is the next theorem. Where a function f is defined from union I is equal to 1 to infinity, that is countable union of ei, where ei's are measurable sets. So it is clearly given ei is measurable set and the function is defined from measurable set ei to r. Then the function f is measurable. We have to prove that function f is measurable if and only if f with respect to ei or f restricted to ei for each I is also measurable. So it is generalized case of previous theorem. So f restricted to ei is also measurable. We have to prove. First we have to take the first statement as true. I have to prove second statement is true. In the converse part we have to take second statement is true. We have to prove first statement is also true. So it is just the same logic as we proved for the previous theorem. Now let me go to the proof. Let us assume that first statement is true. That is, let f from union I is equal to 1 to infinity ei to r is measurable. Is measurable. What we have to prove is to prove that f restricted to ei is measurable for each I. So this is logic, right? So we have to prove this. Where moreover in the question itself it is clearly given ei's are all measurable, right? Now since what we have assumed is ei to r, that is f is measurable, right? Now as per the definition of measurability of a function, just now I have explained, I can write as per the definition of measurability or characterization of measurable function, I can write x belongs to, since just revise the standard definition, if f from e to r, then for any alpha belongs to r, I can write x belongs to x belongs to E, first element, such that f of x greater than alpha is measurable. This is what the definition of is measurable. This is what the definition of measurable function is. So I am going to apply the same concept here. Now in place of E you have union. So let me write union I is equal to 1 to infinity ei such that f of x greater than alpha is measurable. This is what we have assumed. We have to prove f with respect to ei, that is f restricted to ei is also measurable. Right? Now I can clearly write union of our I'll just tell you what we have to prove is in place of union of ei, I have to prove ei. That's all, right? See here, f restricted to fi measurable we have to prove. Meaning is I have to prove for any element x belongs to ei, f of x greater than alpha I have to prove. Now I can write x belongs to E1. For a first case I'm going to prove. For the first element I'm going to prove. If it is true for I is equal to 1, I can generalize the case. So let me take E1. F of x greater than alpha. I can write this as x belongs to union I is equal to 1 to infinity ei f of x greater than alpha intersection with E1 I can write. Just now I have explained in the previous case. So as x belongs to this set, it will be belongings to one of the element E1, right? So I am going to take the intersection with the same element. Again you will be getting even, so it doesn't make any difference. So I can write this as this will be the generalized case of the previous theorem. You just go to the previous theorem. If you understand that theorem, you will understand this. So x belongs to union of all the EIs means when you are going to give I is equal to 1 for particular one set, even intersection even you are going to get, again it will be even. So I can rewrite this as this. Now as per what we have assumed is it is measurable, that is the term in RHS is measurable as per our assumption. So if a term in RHS is measurable, I can say LHS is also measurable, or in other words I can say x belongs to E1 such that f of x greater than alpha is measurable. Meaning of this is f restricted to E1 is measurable, right? In the previous theorem I have told you clearly, if this was the case, then since it is true for first element, so it will be true for all generalized case. Similarly I can write similarly, I cannot prove for all I number of open sets E, right? So it is generalized case. So let me generalize. If f restricted to E1 is measurable, I can say f restricted to EI is also measurable. So this is what we have to prove. Fine. Now for the converse part, first we have assumed f is measurable. What I have arrived is f with restricted to EI is also measurable. For the converse part, let me prove the reverse. Let me assume let f restricted to EI is measurable. What I have to prove is to prove that f from union I is equal to 1 to infinity, EI to R is also measurable. Fine, this is what I have to prove. Clear? The minute when you write this set is measurable, the concept that should come to your mind is I have to prove that x belongs to first set, that is union I is equal to 1 to infinity EI such that f of x greater than alpha is also measurable. So we have to prove this concept. This concept should be there in your mind. Fine. Now what I have assumed is f with respect to EI is measurable, right? So let me take this as G. Let Gi is equal to, it is just a generalized case of previous. So I have done the same in previous theorem also. So Gi as f restricted to EI is measurable. We have already assumed this. Now I can write x belongs to union I is equal to 1 to infinity EI such that f of x, this is what I have to prove. So let me assume that I can express this as union of all EIs, right? I'll just explain. See here, what I have, the meaning of this statement is, since x belongs to union of all the EIs, it is same as I have just taken union outside, so I can write this as x belongs to EI. So one of the EI at least it should be there, or one of the EI should contain xi, right? So I have arrived this statement. Now you can clearly note that except union, this term is measurable, right? Why? Because Gi of x is measurable, I have assumed. So union of, I can write this as union of all measurable functions. So I have already proved union of measurable function is measurable, right? Union of all measurable function is measurable. So what we have in LHS, x belongs to union I is equal to 1 to infinity EI such that f of x greater than alpha is measurable. Meaning is, what I can write, f is defined from union I is equal to 1 to infinity EI to R is also measurable. Clear? So this is what the converse part is. What I have assumed f with respect to EI is measurable. I have proved f defined from EI to R is also measurable. Please go through the first statement, first theorem, then only you will understand this. This theorem is just a generalized concept of whatever the first theorem I have done in this. The next theorem is, if f and g are two measurable functions which is defined in a measurable set, that is real number R, then we have to prove that for any element x belongs to E, f of x greater than g of x is measurable. Now coming to the proof, let me define a function or a set AR in such a way that x belongs to E such that g of x less than or less than f of x for each rational number R. Why I have defined this function is, see, I can rewrite this as R less than f of x, or else I can write f of x greater than r, right? Similarly, I can write g of x less than r. So you can compare these two. Suppose if r value is 5, so f of x greater than 5, g of x less than 5. Meaning is, by comparing these two, less than in the sense at least it should be 4, right? So meaning of this statement, what I have assumed is, comparing these two, I can write f of x is greater than g of x. Fine. So that is what the given set is. I have rewritten that as r. I mean, r is an element which is in between g of x and f of x. Moreover, f of x will be greater than g of x as per the given condition. So I have rewritten the given set in this form. I have considered that as AR. Fine. Now again this set AR can be written as x belongs to E such that g of, I'm going to split this. Just now I have explained, no? So likewise I'm going to split it. So I'll get intersection x belongs to E such that f of x greater than R. Just whatever the statement I have rewritten this statement. I mean, I can split this and I'm going to take intersection. Fine. So that there will be whatever the elements are there, that all the elements will be included in this assumed set AR. Clear? Now you can clearly observe that in the theorem of what we say characterization of measurable function, the very second class, I think so, of the measurable function, I have already proved that f of x less than r and f of x greater than some alpha, where r is real number, but in the standard theorem we have alpha. So I have already proved that this is measurable and this is measurable. Or else I can say total RHS value, intersection is also measurable, right? So RHS is measurable. Fine. Why? Because it is intersection of two measurable set is always measurable. So I can say RHS is measurable. Thereby AR is also, if RHS is measurable, I can say LHS is also measurable. Fine. Now what I'm going to do is, I have proved that AR is measurable, where AR is g of x less than or less than f of x. Now let me consider a set x belongs to E such that f of x greater than g of x, the given set. Fine. What I have proved is the set AR is measurable. Now I have to prove that this is also measurable. I have considered the same set and I can write this set as union of all the AR such that g of x less than or less than f of x. Why? Because I have considered AR as g of x less than or less than f of x. I have written the condition here, and it is the union of all AR. When you are going to consider union of all the sets AR, it will be satisfying this condition. I have given simple example here. Suppose if you are going to take R as 5, g of x should be less than R. In the sense, g of x should be, let me take minimum value 4. By comparing these two, I can clearly say f of x is greater than g of x. So I am going to express this as union of all the AR. So AR I can write like this. Again, it satisfies the given condition. So I can say union of all AR will be given set f of x greater than g of x. Fine. Now I have proved that AR is measurable. Fine. I have already proved AR is measurable, and again I have expressing that as union of measurable set. And you already know that union of measurable set is measurable. Fine. So union of measurable set is measurable. This theorem is already proved. By that I can say LHS, since RHS is measurable, I can say LHS is also measurable. What we have in the LHS, x belongs to E, f of x greater than g of x is also measurable. So this is what we have to prove. X belongs to E, f of x greater than g of x is also measurable. What I have assumed is, I have taken a set in such a way that it contains all the values satisfying the given condition, that is f of x greater than g of x. I have assumed for all the values or. So again I have splitted this and I have proved that AR is measurable. Now given set can be expressed as union of ARs. Why? Because AR contains all those elements which satisfies the given condition f of x greater than g of x, as I already told you by taking the counter example. Again it is a since I have already proved AR is measurable and I have expressed the given set as union of all the measurable set, and by the theorem union of all the measurable set is also measurable. Meaning is RHS is measurable, I can say LHS is also measurable. In the LHS what we have, x belongs to E, f of x greater than g of x is also measurable. Clear? Now let me prove the same theorem. In this case you have f of x less than g of x, but here I have f of x less than g of x. Reverse of this. In the first theorem what I have proved is f of x greater than g of x is measurable. Same condition I am going to use same concept and I am going to prove f of x less than g of x is measurable. Same statement, only inequality is changed. Fine. So I am going to prove by using the same concept. Let me prove that. So as I done for this theorem, let me assume the same, that is same set AR can be defined as x belongs to E such that f of x less than or less than g of x. I have to assume. Only difference is in assuming the set AR. In the first theorem I have assumed g of x less than or less than f of x. So that I have obtained f of x greater than r, g of x less than r. Suppose if you are going to take f of x, r is equal to 5. I am explaining for this theorem. Suppose if you are going to take r is equal to 5, then f of x greater than 5. But f of x should be less than 5. Right? So meaning is f of x is greater than g of x. This condition is satisfied. But this case, in place of g of x, I have written f of x. Now coming to the theorem, see here, meaning of this is, suppose if I am going to take r is equal to 5. So I am going to split this as f of x less than r less than g of x. R less than g of x can be written as g of x greater than r. Since r is equal to 5, so meaning is f of x is less than 5, g of x is greater than 5. So by comparing these two, I can say f of x is always less than g of x. It is just a reverse of a previous theorem. So I have explained expressed the given set in this in the form of all the numbers, rational numbers r. So I have taken that set as AR. Now I am going to split this. That is what I have done in the previous theorem as well. So let me split this. AR can be written as x belongs to E such that f of x less than r intersection with x belongs to E, g of x greater than r. So I have written here clearly g of x greater than r. I have split this. Now by the characterization of measurability of a function, I have proved this. First set is measurable. F of x less than r measurable, f of x greater than r measurable. Anyhow, whatever may be the function, if it is greater than real number or rational number, it is measurable. I have already proved this. Now AR is expressed as intersection of measurable sets, right? Intersection of two measurable sets. Again, by the theorem, I can say intersection of measurable set is measurable. By that, I can say total RHS is measurable. RHS is measurable. So if RHS is measurable, I can say LHS, that is AR is measurable. AR is measurable. Fine. Now let me consider the given set x belongs to E such that f of x less than g of x. Now I can express this as union of all the ARs, where r is in between f of x and g of x. If you want, you can write, or else you can write as it is. So I can express the given set as union of all the ARs as I explained in the previous theorem. It is also same. Now you can note that AR is what we have already proved is AR is measurable, and we know that countable union of measurable set is measurable. I have already proved the theorem, countable union of measurable. I'm not going to write all the statements here, but anyhow I'll send you the notes, but you just listen to me. So countable union of measurable set is measurable. By that I can say RHS is measurable. So if RHS is measurable, I can say LHS, that is the set x belongs to E, f of x less than g of x is also measurable. So I have proved the theorem. Clear? First case I have proved for f of x greater than g of x. In the second case, f of x less than g of x. Now based on this theorem, I am going to prove the corollary of the same theorem. We have a corollary. Here is a statement of corollary for this theorem. So corollary says that if f and g are measurable function which is defined on measurable set E, then I have to prove that f of x less than or equal to g of x and also x belongs to f of x is equal to g of x are measurable. In the previous theorem, what I have proved is less than, and before that I have proved the same for greater than, right? So here I have proved for less than. In the previous theorem I have proved for greater than. Now I am going to prove the corollary which says that when you have less than or equal to and is equal to, the statement holds good. This is what the corollary is. Now coming to the proof. First let me prove less than or equal to inequality. So let me consider the statement x belongs to E, set proof. X belongs to E, f of x less than or equal to g of x. Now meaning of this statement is f of x will be always less than g of x. In the sense, in certain case it may be equal, but it is always less than. Fine. However, whatever may be the value of g of x, f of x is less than g of x, right? However, I can write this as intersection of n is equal to 1 to infinity, that is countable intersection. When you have infinity, I can say it is countable intersection x belongs to E such that f of x will be less than g of x plus 1 by n. I can write like this, right? Why? Because I have used the same concept in so many theorems. I will just explain here. Since f of x is already less than g of x, if you had a small quantity, say 1 by n to g of x, it is almost less than it, right? It may be equal in certain cases, right? When you're going to add some value, it may be equal. So, but it always less than. Why? Because it is, first of all, in the given set itself, it is less than g of x. A function f is less than g of x. If you add certain value like 1 by n to g of x, again it will be less than g of x only. So, I am going to take intersection over all those values. Fine, so I can express this set as intersection of this value. Now, you can note that RHS is expressed as countable intersection, I can say. If you understand the previous theorem very well, then only you can understand this. Please go through all the videos, you will understand. Fine. So it is countable intersection of measurable set. So countable intersection of measurable set is again measurable. So I can say RHS is measurable. If RHS is measurable, clearly LHS is also measurable. That is x belongs to E, f of x less than or equal to g of x is also measurable. Is also measurable. Clear? Now let me prove for equals. First one is finished. Now second one I have to prove it is for equals. So let me write the statement. X belongs to E, f of x is equal to g of x. And remember, when you have equals between two function, I can express the function relation as less than or equal to and less than. Difference of less than or equal to and less than. In the sense, I can rewrite this statement as x belongs to E such that f of x less than or equal to g of x minus x belongs to E such that f of x less than g of x. So when you subtract these two sets, you will obtain all the values of f of x will be equal to g of x. Fine. Now just now I have proved that less than or equal to g of x is measurable. So in the previous theorem I have proved that f of x less than g of x is also measurable. Here I have proved, see here, x belongs to E, f of x less than g of x is measurable. So it is measurable, we have proved. So I can express equals as difference of measurable set, right? So this is already proved and this is also already proved that they are measurable. So I have expressed it as difference of measurable set. Difference of measurable set. And by the theorem, difference of measurable set is again measurable. That is RHS is measurable. Right, if RHS is measurable, I can directly say it is just a logic. You have to understand the concept, right? So f of x is equal to g of x is also measurable. Clear? I have used the previous theorem as a corollary. So this is the theorem. Theorems on this completes the theorems on measurability of a function, and you left with only single concept, that is called a step function. And one more theorem on step function. That will be the last concept of second unit. Let me continue in the next session. Hope so it is clear. Further, if you have any queries, you can free to ask me. Thank you. Continue in the next session.